Hello. Well, we have a set of long lines in the left image and the right image, and we've made some correspondences between those using our stereo correspondence constraints. What we're interested in now is trying to take those correspondences that we've got in the two-dimensional images and build a three-dimensional representation of the line out of them. And the reason for this is we're sort of heading towards doing some matching, where we're going to have a three-dimensional model with three-dimensional lines, and we want to be able to match like for like. And therefore, we're going to look at the three-dimensional lines that we've extracted from the correspondences in the image to match those with the three-dimensional lines that are in the model. So we need those lines, those three-dimensional lines, from triangulating the two sets of paired edges that we found. So that's what we're going to do in this little segment of video. Okay, so as I've said, we've got our successfully paired lines right there, and we're going to do this really in two steps. Okay, first we're going to take each of the individual lines and project that into a plane in space, and then we're going to look at the intersection from where those two planes are. And we know from just sort of simple school geometry that the intersection of two planes is a line, and that's going to be the three-dimensional line that we're interested in. So let's do that kind of a little bit geometrically and also sort of pictorially. Okay, so here's my camera again. Here's my camera origin. Here's the line that I see in the image. And that projection point and this line defines a plane in space. Okay, and it sort of goes out to infinity. Now we know that the three-dimensional line that we're looking for is going to have to lie in that plane somewhere. So here's that 3D line. We know it has to lie in the plane because that whole plane projected down onto this line in the image. So we know it's got to be out there somewhere. We just don't know exactly where. Okay, well, we're going to have our equation of our line. Again, here's the equation of the line. We're going to represent it in homogeneous coordinates. So here's our points A, B, C, and here's the equation that we've got right here, okay, for that line. And we've got our projection matrix that we've had previously, and that's our projection matrix P. And then it turns out that the equation of that plane that we've got right there is given by this particular product between the line and that matrix. Okay, so we're going to do that for the left image, and we're going to do that for the right image independently, this sort of line finding and projection right here. And now we want to find the intersection, which is the three-dimensional line. Okay, and here's our sort of geometry of that again, our two cameras, the left and right cameras. Here's our planes projecting out there, and where those two planes project, that's our 3D line. And it makes sense because here's the line in this plane, and it projects down to this line. Here's the line in the other plane, and it projects down to that line right there. Okay, so how are we going to do all of this? Well, one of the things that we need to do is we need to get some correspondences or whatever here, and we're going to have to sort of pair up points between the left and right line. That's going to be our approach to do that. And the way we're going to do that is we're going to take the midpoint of the left line, and using our fundamental matrix again, we're going to predict the corresponding point over in the right image, and then we're going to compute a second point on the left line right here. So we've got our direction vector for that line. So just by taking the midpoint, adding a little bit of that direction vector, that gives us a second point. And again, with our fundamental matrix, we can get a corresponding point on the second line. So we've got a couple of matched points on the left line and the right line. We're going to use that in our geometric calculation right here. Okay, so let's do that in a little bit more detail. Here's our paired lines. We've got our midpoints from the left and the right. Here's our direction vectors from the left and the right, and we've got our fundamental matrix. Okay, well, we're going to extend this to a homogeneous coordinates, so that's for this point right here, it's sort of C. For the direction vector, it's U. We've got to extend it. In this case, we have to extend the U, the direction in two dimensions to make it in a homogeneous coordinates. We extend it with a 0. We get our projective description of the line in the right image, and that's given by these values right here. It's three numbers. And with this projective matrix, we're going to want to intersect what we're going to want to do is we're going to do sort of an intersection between the line, the point in the left image, our midpoint, and the corresponding line in the right image. We're going to want to find the corresponding points. We're going to do this by intersection using the fundamental matrix. Okay, and the way we're going to do that is, okay, we take the line in the right image, we're going to turn it into its sort of skew form, and then we can do our prediction right here. So we take our point in the left image, we apply the fundamental matrix to it. That gives us a line in the right image. We're going to intersect that line in the right image with that skew matrix that we've just got, and that gives us a point with homogeneous coordinates. And then we need to turn that down into a point in the image coordinates, and that's so we sort of normalize it with the third coordinate right there. Okay, so that gives us our point PM. We do the same thing again with the second point in the left image. So the second point is going to take the midpoint, and we're going to take that direction vector that I talked about, U, and we're going to add a little bit of an offset to it. Okay, and that's this offset. We're going to do that same projection with the fundamental matrix and intersection with the line in the right image. It gives us another point. Again, we do our normalization with that third coordinate. So that gives us how we go from the 2 points, the midpoint and a little offset point in the left image, to a corresponding pair of points in the right image. Okay, and now we're in a position to get a little bit of, we can do our triangulation, okay, between the corresponding points. So there's the left-right pair in the first and the second left-right pair, and we can do that triangulation to get our 3D points, sort of G and H, and then with that we can then estimate an estimated three-dimensional midpoint of that line right here, and that's sort of the G point, and we can estimate a direction in 3D for that line right here as well too. Okay, and that's just by looking at the 3D vector between those matched points that we've triangulated right there. So that gives us a three-dimensional midpoint and a three-dimensional direction vector that we're going to be able to use. Now, one of the things that we didn't really quite go through here, right, as I said, we're going to take these points and triangulate them. Well, I didn't really give the details here, and that's what we're going to do next, is how to triangulate those 2 points from the left and right image and get the three-dimensional point about it. That's a little bit sort of messy, and that's what we've gotten right here. So we're going to start with our projection matrices, we're going to start with our camera intrinsic matrices, and we're going to start with our points right here. And we want to now therefore compute these points right here by the projection matrix. Okay, and that's what we've done right here. Okay, and what we want to do is we want to produce this point G and this point H, okay, given by that projection. There's sort of a little bit of a complication here. I think I've overused the variables G and H. These are not quite the same G and H as previously. I apologize for that. And when you see the slides, I'll get that sorted out in the future. But here in the video, I'm just using G and H. Okay, and with that, then that gives me a set of algebraic quantities A1, 2, 3, and 4. And I can create a little vector out of that, a matrix. I can do a singular value decomposition on that. And then once I have done that singular value decomposition, then I get, I can read off effectively the three-dimensional vector from that. So it's a little bit of messy algebra right here, and we don't need to go through the detail of exactly why this works, but this is what we need to do to translate from the left and right point in the images into this three-dimensional coordinates here using all of these matrices that we found previously. Okay, so here we've got our corresponding points and our corresponding midpoints. We can do a little bit of a zoom on those. Here you can see the lines. Here you can see the corresponding midpoints of the segments that we've successfully matched together. And we've got most of the segments have a matched midpoint that is pretty close to the correct point. Sort of all in here. This is for the left image and for the right image. For the right image, it's not quite as good. Here's one of the line segments that's I got a mismatched point right here, and similarly there's one along here that's got a mismatched point, and that's arisen out of all of all the many extra edges in the little edge fragments in the image, meaning that we haven't been able to successfully match and estimate exactly the desirable length of that little edge segment. It's kind of gone on a little bit too far. Here's a little bit of a zoom on those segments right here, and we've got them sort of lined up and numbered here. We're going to use these numbers in the matching to help give us some idea of how well our three-dimensional calculations have gone along. And so that's from one block. Here's from the other block in the upper right corner of the image. And what we're going to look at here is not really the three-dimensional position, but we're going to look at the angles between pairs of lines. Okay, so here I'll just do the left lines. Okay, so if we go back to the left block, you'll see here's line number 1 and here's line number 6. And knowing what we know about these sorts of blocks, we would say that this should be a 90-degree line, or a pi/2 radians angle between them. And so we can now look at what calculation we get. So the angle between these two, it should be pi/2, that's this number here. If we actually look at the calculated angle between these two line segments, we get 1.52. That's actually, considering all the errors that could possibly go wrong, and the noise in the images and the little imprecisions with edge detecting and line finding, that's pretty remarkable. Maybe a more typical case is the next two. So these should be 1 in 24 and 1 in 42. If we go back, 1 in 24 or 1 in 42, these are lines that are parallel to each other. So the angle ought to be 0. And in fact, we do see the prediction is 0, and they're kind of close to 0, but this is sort of more of a typical kind of error that we get from that. There's a variety of things you could say about which angles would be more likely to be more accurately estimated or not, but that kind of depends a little bit on how vertical the edges are, but we're not going to worry too much about that. What we just can say is if you scan down looking at all possible pairings between the lines on either the first block or the second block, if you sort of scan down the list, what you'll see is that all of these angles between the lines are actually remarkably close to the correct angle. So the computed angle is quite close to the true angle. And I've just kind of included all of them here sort of for the sake of completeness, but we don't need to look at all the details there. Okay, but what the conclusion that we can make is that with this triangulation process, we've actually done a pretty accurate job of estimating the three-dimensional orientation, at least, of the lines. And it turns out that the position is also reasonably accurate as well. Okay, so what have we got right here? It's really a nice, straightforward algorithm. Some of the geometric algebra is a little bit complex in the middle, and I haven't gone through all the details. I've just kind of given you the formulas. But it's based on the fundamental concept that if I've got a line in this image and a line in this image, the back projection of those lines turn into planes, and where those planes intersect in space, that has to be the line that we're looking for, the three-dimensional line that we're trying to reconstruct from the paired two-dimensional lines. Okay, so we've looked at a little bit of the geometry of the back projection. We also looked at a little bit of the algebra of the back projection, so we can actually do that calculation, and then and we can see actually the results are pretty reasonably accurate, considering all of the imprecisions that we've got right here. Thank you very much.